Logistic regression is a method used for binary classification, predicting the probability of an instance belonging to one of two classes. It employs a logistic or sigmoid function to transform a linear combination of input features and parameters into a probability score between 0 and 1. The model then classifies instances based on a chosen threshold. It will offer a prediction of 1 if the model output is over that threshold, and a prediction of 0 if the model output is under the threshold. In binary classification problems, we have data with labels from just two categories, and the objective is to train a model to differentiate between the two. And so, for example, we could have a problem to decide if a picture is that of a cat or of a dog, whether the tumor in a scan is malignant or benign, whether the product in a picture is scratched or not, whether the traffic light is red or green. And the two classes are typically encoded with 0 and 1, and they are referred to as the positive and the negative class. And in this lecture, we are going to discuss the simplest model for binary classification, which is logistic regression. Simple as it may be, logistic regression is a very popular choice in binary classification problems, and it turns out to be quite a powerful machine learning model. It's very similar to linear regression in the sense that its classification decision is based on a linear combination of the features of the data points. So here is an example. We have some scans of some tumors, and we aim to predict the tumor type, whether it's malignant and benign, as a function of the size of the tumor. And in this example, we are going to label the benign ones as 0 and the malignant ones as 1. And for example, here is the data that we may have in this example. So we have 4 samples that are benign, so they are labeled with 0. So I'm just having them on this horizontal corresponding to level 0. And we have 4 samples of different size that are labeled as malignant, and so they are displayed in this plot on this horizontal corresponding to level 1. And if you were attempting to train a linear regression, the result of that linear regression would be this, that you would have a model that attempts to go as closely as possible through these data points, and the result is likely to be something like this. This model has at least a couple of obvious difficulties. The first one is that the model is going to predict arbitrarily large values and arbitrarily small values in between -infinity and +infinity, being a linear model. But in fact, our data set only has labels that are either 0 or 1. So that's going to provide us with some difficulty relating the output of the model to the 0-1 labels we have in our data. The other difficulty is that this model doesn't seem to really capture the trend in our data. It's just a straight line, whereas our data seems to be rather more distributed like a step function. We have a bunch of data points here on this lower horizontal, and then there is a jump at some point, and it goes to this higher horizontal. So a model that really would come closer to the pattern in the data would resemble more this sort of step function that's based on a threshold, and then it jumps from 0 to 1 once it crosses that threshold. So to address these difficulties, we have these 2 questions that we need to answer. One is that we would like to predict only values in the interval 0, 1, ideally just values 0 or 1, but I will make the point in just a moment that even with predictions in the whole interval 0, 1, we will do fine. So we will need some sort of a simple solution for how to turn the unconstrained output of a linear model into an output that comes only in the interval 0, 1. And the other thing that we would like to get is to obtain this sort of step function that was suggested by the data distribution in our example. So a simple solution to these difficulties is to filter the output of the linear regression model through the so-called sigmoid or logistic function. And this function has the form sigma of x equals to 1 over 1 plus e to power minus x. And its plot that you can see on this part of the screen resembles the step function that we were aiming for. Now, this function will take only values in between 0 and 1, and for negative x, the sigma x is going to be less than 0.5, and in fact the values are going to be closer and closer to 0 as x approaches minus infinity. On the other hand, for positive x, the values of the function is going to be larger than 0.5 and is going to approach value 1 as x is approaching plus infinity. So for our example, this works very well because this allows us to really produce a model that looks like this. So it has the shape of the sigmoid function and is going to switch from 0 to 1 exactly in the way that the data is suggesting, based on this sort of sigmoid shape that this plot has. So the idea in logistic regression is that we would use a linear model, just a linear combination of the features, just like we have done in linear regression, but we will take its output through the sigmoid function. So the model is going to be something like this. It's going to be a function applied to these features of our data point, and the output of the model is going to be we take a linear combination of the features and then we pass it through the sigmoid function, and the output of the sigmoid function is going to be the prediction of the model. So obviously, if we do it like that, the model output is going to be in the interval 0 and 1, and we will have to interpret this as being either label 0 or label 1 because the encoding of our data was in terms of labels either 0 or 1. And this in fact can be done in a very easy way. You can just think about the output of the model in terms of a probability score, answering the question, is your label 1? And for example, if the output is going to give you a response of 0.85, remember the output is a number between 0 and 1, you can interpret that as the probability of x having label 1 being 0.5 or 85%. And obviously the other way around, the probability of that particular point having label 0 is exactly 0.15 or 15%. So in general, we can just do it like this. If the output of the model is larger than a certain threshold, let's say 0.5, but you can also choose another threshold depending on your data distribution or the details of your application. So if the output of the model is larger than the threshold, let's say 0.5, then we're going to interpret this as a prediction that the label of x is 1. And of course, reversely, if the output is smaller than the threshold, let's say smaller than 0.5, then we are going to interpret this as a prediction that the label of x is 0. Now, this also means, remember that the sigmoid function is larger than 0.5 exactly when the argument of the sigmoid is larger than 0. And in logistic regression, the argument is just a linear combination of the features. So this sort of classifier decision is exactly the same as saying we are going to check if this particular linear combination that the logistic regression model is based on is larger than 0, then we are going to interpret this as a prediction that the label of x is 1. And reversely, if this linear combination of the features is smaller than 0, then we are going to interpret this as a prediction that the label of x is 0. So the consequence obviously is that logistic regression is going to separate the two classes with a line, because as we know from logistic regression, this sort of linear combination of features is exactly describing the equation of a line. And when you check whether the linear combination is larger than 0 or smaller than 0, effectively what you are doing is you are checking in which side of the plane your data point is. It's on either on the one side of the line or on the other side of the line. So here is one example for how this would look like. If I'm choosing my data points to have two features so that I can just draw them easily on this plot, and we have the data, for example, like this, if I'm just denoting here, this would be 1 and this would be 1. And so we would have, for example, some data points somewhere here. This would be one class, and maybe the other class would be data points coming somewhere here. So with logistic regression, the decision boundary would be to find a line, for example, this line that separates the two classes. So all the points in the 0 class would be on this side of the line, and all the points corresponding to the 1 class would be on the other side of the line. This particular line that I drew in this example corresponds to checking whether x1 plus x2 minus 1 is larger than 0 or it's smaller than 0. So depending on the sign of this combination of the features x1, x2, so this is feature x1 and this is feature x2, you are either on this side of the line or on the other side of the line. As a matter of fact, logistic regression is a very powerful technique, and we can in fact have much more complex decision boundaries than just a line with just a little bit of extra effort. And I just want to show you an example of how this could be done. For example, again, if I'm drawing the axis, and again I'm going to have two features so that I can draw this on the screen, and I'm just denoting this would be 1, 1, here would be minus 1 and minus 1. And so let's just assume that this time I have some data that's distributed here. This is one class, and the other class is going to be, somewhere here. Obviously you cannot separate these two classes with just a single line, but you could in fact separate them with a circle that goes like this. And the equation of this circle is exactly x1 squared plus x2 squared minus 1 is equal to 0. So your decision would be to check whether x1 plus x1 squared plus x2 squared minus 1 is larger than 0 or not. And depending on this, you would classify your data point as being labeled 0 or label 1. The main point I want to make with this small example is that this in fact can be done with logistic regression. There is only a small trick that you have to do, and that is that instead of your data point having features x1, x2, you are going to have a sort of a transformation where you think about features x1 squared and x2 squared. With this small trick, all of a sudden your decision boundary, which is now a circle, is in fact a linear combination of these features x1 squared and x2 squared. The point being that you can apply logistic regression on these transformed features and get a decision boundary that's a circle. So again, my point being that logistic regression can be a very powerful technique. It can have decision boundaries that are more complex than just a line, with just a little bit of extra effort. And of course the question is going to be, how do we learn a classification model? How do we train a logistic regression model to find the optimal decision boundary? And the answer is that you can do that with gradient descent in a very similar way as we do for linear regression models. The only difference is that the cost or the loss function will have to be chosen in a more careful way. And that's what we are going to discuss in the next video.